All right, so yesterday we left off here where we were talking about Dalton's atomic theory, and then we talked about that Dalton really didn't have an answer for the question of what does an atom look like. Okay, he had all these great ideas about how an atom behaves and how it governs the structure of matter, okay, and things like that. Those were all good ideas. We still generally find them to hold true, but obviously the idea that the atom is a solid sphere does not hold up. Okay? It doesn't hold up because a lot of experiments performed after he came up with that model suggested that there's more than just one part to an atom. Okay? The behavior of certain things in reactions and stuff like that basically said there's no way there can only be one part because it doesn't account for this and this. All right? One of the first experiments that really, let's say, contradicted what Dalton said was J.J. Thomson's experiment in electrochemistry. Right? He was essentially doing experiments involving reactions that produced electric currents, playing around with improving batteries and things like that. And what he discovered is certain chemical reactions will produce an electric current. Well, Dalton's solid sphere model doesn't explain where the electricity comes from. Because what is electricity? Right, it's moving charges, specifically electrons flowing through a wire. Okay, well, a solid sphere does not account for charges moving through a wire. So he said, all right, it's obviously not the atoms themselves. They're not moving through the wire. Okay, how did he know that? How did he know it wasn't there? Okay, partially, yes, but he didn't know about electrons yet. How did he know that the actual spheres weren't moving through? Exactly. Whatever he was working with would disappear. The mass of the stuff would change because atoms would be moving. So he knew it wasn't these solid spheres moving through. There must be some part of the atom, okay, that was able to come off. So he said, all right, here's what we'll do. We need to account for the fact that there's negatively charged particles. But atoms are electrically neutral, so there has to be some positive there to offset it. So what he said is, I'm not going to totally destroy Dalton's solid sphere. I'm going to keep that. But I'm going to say that embedded on the surface, loosely embedded on the surface, are negatively charged particles. And I'm going to call them electrons because they're what makes electricity, and that name makes sense. All right? And then I'm going to say that the rest of the sphere is positively charged, and that's what makes the charges balance. All right? And at the time, people were like, that seems like a really logical idea. That really accounts for what your experiment said. And it still keeps Dalton's model, which is nice because we kind of like him. The last 200 years we've been dealing with this model. Okay, so what he basically said is, in a reaction, something happens that causes these electrons to fall off, and then they can move through a wire to another position, essentially to another atom, because that's what happens. Okay, so some atoms lose electrons and some atoms will gain them, and that's kind of how the electricity flows through. Right? So his model fully explained how that was going on. Now, this is 1897. Over the next 50 years, things changed often, and there was a lot of chaos in the scientific community about what does an atom really look like. Okay? Because this is where kind of the nuclear age began. Okay? Well, not in 1897, but shortly thereafter. Okay? People started doing a lot of studies about the behavior of matter and the structure of the atom. And what they were finding was this whole idea of one big mass, even if it had little electrons on it, does not account for all the mass involved. Okay? He said, yes, there's a positive charge there. Maybe there's many positive charges, just like there's many negative charges, which would mean there has to be small positively charged particles. Okay? But when they started coming up with that idea, the problem was these particles had to be huge. Well, I mean, huge on a tiny scale. That doesn't make any sense. They had to be really big on an atomic scale, all right? And the behavior of matter didn't really agree with that. So over the next little while, people were discovering, okay, there's protons, there's these small positively charged particles, okay? But what does the atom look like? Now is it a solid sphere with a proton and an electron embedded in it? So now there's positively charged things and negatively charged things. And people said, well, no, that can't be right, because if there were positively charged things embedded on it, they could fall off too. And people knew positive charges didn't move around. Positive charges always stayed put. Okay, so there came to be quite a bit of argument about how the atom looked. Okay, shortly thereafter, okay, the neutron was discovered as well, and that helped to kind of account for the mass of the atom. But people still didn't really have an agreement on what does the atom look like. Is it big and solid? Is it small and made of a lot of empty space? What does it look like? Okay. So we got Chadwick here, who discovered that protons weren't the only ones. He was basically the one who discovered the neutron. Okay, carries no charge. Neutrons and protons are exactly the same size. Okay, just one's positive and one's neutral, right? They stick together. Okay, so finally, a guy comes along by the name of Ernest Rutherford, and he says, I'm going to perform an experiment that will essentially tell me how big atoms really are. It won't tell me really what they look like, but it'll give me a pretty good idea. I'll be able to make some assumptions about what an atom looks like because I'll have an idea whether it's solid or whether it's made of a lot of empty space. Okay, solid may not be the right word, but I mean like kind of large, all right? So what he did is he set up an experiment where he had an extremely thin piece of gold foil. Okay, it would have looked similar to like what you have at home, tin foil, all right? Except it would have been way, way thinner and made out of gold. Okay, so this thing was so thin that it was really only maybe about half a dozen to a dozen atoms thick. So very, very thin. Like if you had it sideways, you wouldn't see it, kind of thing. Okay, so it was a very, very thin piece of gold foil. And he said, I'm going to put an X-ray machine in front of it, and I'm going to shoot X-rays at this foil. If atoms are really, really small, then, and there's lots of space between them, then all of the X-rays will go right through the gold foil because there'll be so much empty space. If atoms are really, really big, then most of the X-rays will bounce off the foil and come back. Okay? His belief was all the X-rays were going to get through. Okay? So he set this kind of thing up here. All right, so he had an X-ray machine here. He had the thin gold foil, and then wrapped in a circle around it, he had photographic film. You guys know what that is? You're of the digital camera generation, okay? But back in the day, cameras had this stuff called film in them, okay? Yeah, all right. And when you shine light on the film, any kind of light, X-rays, doesn't matter, it changes color. So he would know any spots where the X-rays struck because they would have a bright spot in that area, okay? So what his experiment showed was that some of the X-rays did go through. In fact, many of them went through. But some were deflected slightly. Some were deflected a lot. Some ended up like way over here. Some like behind the gold foil even. Right? He said the only way that could happen is if the X-rays were actually hitting atoms and being deflected as a result. Okay? Because X-rays are light and they're made up of things called photons, and photons are essentially light particles. Right? So it would hit them and they would bounce off in different directions. Still, the bulk of them got through. So what that told him was there's a central dense part to an atom, and then there's a lot of empty space around it. The empty space is filled with electrons because we know they can be lost and gained. So they must not be part of the central mass. Okay? We know the positive charges never move, so they must be in the middle along with the neutrons. So he essentially proved the idea of the nucleus. Okay? Rutherford is responsible for the modern nuclear model of the atom, which makes him extremely important. Okay? So Rutherford, okay, nuclear model. So important, but when he drew up what he thought the atom looked like, it's actually not right. I mean, it's right in a very basic sense. The protons and neutrons are in the nucleus and the electrons are on the outside, okay? But after his experiment, and still to this day, the argument is, what are the electrons doing? Right? We know the protons and neutrons are all stuck in the middle. They don't do anything. It's fine. That's easy. Okay? But what are the electrons doing? Do they orbit like planets at different distances? Do they all orbit at the same distance? Do they move around? Nobody could really tell. Okay? So what Rutherford said is, it looks like this one. This is the Rutherford model here. Okay? He said that there's the nucleus, and then all the electrons orbit at the same distance, but their orbits are offset at different angles so they don't run into each other. Okay? Which we know now isn't true. Right? But people accepted it at the time because his experiment said electrons aren't in the nucleus, protons and neutrons are. Okay? Questions so far on that? Okay, so this experiment is probably something you should make note of. Right? It's a pretty important experiment. It led to the development of the nuclear model. So Rutherford, gold foil, nuclear model, okay, pretty important stuff. Yes, yeah. Yeah, he came after Chadwick, so he knew about the existence of those two particles. All right, so like I said, the big argument from there on was, what are the electrons doing? Okay? And there were many ideas, and many of them were hard to prove right or wrong. Okay? Bohr was probably one of the most popular models. He had what we call the planetary model, which is electrons orbit at fixed distances, but each orbit can hold many electrons. Okay, and they all stay in these things called orbitals. Okay, and they stay in there and they just orbit like planets around the sun. Problem is his model couldn't explain some very basic things that went on in nature. Right? For example, when a plant makes sugar using photosynthesis, it does so by harnessing energy from the sun. Okay? To harness energy from the sun, what happens is the solar energy strikes the chlorophyll molecules. Okay, and this is kind of simplified a little bit, but this is essentially what happens. Okay, it strikes the chlorophyll molecules, and all the electrons that are on the atoms in that molecule get excited. They gain energy because the sun is shining on them, and they move away from the nucleus because they've gained energy and they're moving faster. Okay, so they have to move further away. When the sunlight is gone, those electrons will move closer because now the energy that was keeping them that far away is gone. When they fall back down, they release the energy they had gained. And that energy is what's used to break apart carbon dioxide and water and put them back together as glucose. Okay, that's where plants get their energy from, or how photosynthesis kind of works. Okay, his model couldn't explain what the electrons were doing in order to make that happen, because it said they stay in place. They orbit, but they don't move up or down. Okay, so if we were to take a picture of an atom, it would look something like Bohr's model because it would be frozen in time. But if we watched it like a video, it wouldn't look like this. It would look like this. Okay, de Broglie came up with what we call the electron cloud, or the quantum mechanical model. And it does explain how electrons can move further away or closer to the nucleus, how they can gain and lose energy as a result of that, and how they can cause certain things to happen. Okay, if you have like any glow in the dark materials on your watch, like some people have watched, they go out in the sun and then they come in the dark and it glows for a little while afterwards. It's the same thing as photosynthesis. The electrons in that material gain energy and move away from the nucleus. When the sun is gone, they give that light energy back. Okay, so as they fall back to the nucleus, they release the light energy and they glow for a short period of time. Okay, same idea. All right, so de Broglie's electron cloud model, it looks like everything is kind of random, but there's actually a very complex shape to the places where electrons can be found, and you'll learn about that in Chem 20. Okay, when you start talking about the orbitals and how this atom can have electrons in this orbital, that orbital, and this orbital, but not this one. Okay, and things like that. And it's all based on how many electrons, how fast they're moving, how much energy they have. Okay, so in de Broglie's model, the electrons can jump or fall from one level to another depending on the energy of the atom. Okay, if they're going to make a move from a low orbital to a high orbital, we call that a quantum leap. Okay, because it's the quantum mechanical model, so it's a quantum leap if they move up. Okay, questions on that? Okay, so that's the last model that we'll cover because it's the one that we currently accept to be true. All right, so you might want to make a note of that. This is the one that we do currently accept to be true, the electron cloud or quantum mechanical model. Okay, so you can see in his kind of picture here that, yeah, there's the nucleus here where all the protons and neutrons are, and then there's a cloud of electrons. Now, there are some regions of the cloud that are more densely populated with electrons than others. Okay, these are the more common lower energy orbitals. Okay, the higher energy orbitals typically have less electrons in them. And there's also a region close to the nucleus where typically electrons don't go. All right. I mean, yes, electrons are attracted to the protons in the nucleus. That's what keeps them from flying off. But when they get really close to the nucleus, the neutrons will actually repel them a little bit. And that's what keeps them all from crashing into the nucleus. Right. Because I mean, if opposites attract, then theoretically all the electrons should crash into the nucleus, but they don't. Okay. There's this kind of strong nuclear force from the neutrons that keeps them away. Okay, so the structure of the atom as we currently understand it is that there is a dense positively charged nucleus that contains the neutrons and protons, and there's a large volume of space surrounding the nucleus in which the electrons can be found. So in fact, atoms are made of a lot of empty space. That's what Rutherford's experiment showed. Yep, there's a central dense nucleus, but how many X-rays were able to travel through all this empty space? Yeah, some of them hit the nucleus and bounced off, but there's a lot of empty space here. Okay, that's what the experiment proved.
What about just like hydrogen? Why don't the electrons crash into the nucleus then?
There's still a strong nuclear force that's present there. It's when you get to physics 30 and you start going over all of that stuff, it'll make a little more sense then. But yeah, there's a what's called a strong nuclear force that keeps that from happening. It's one proton, one electron, right? So, okay. Questions there? Everyone good with that? I suppose yes. The problem with that is that electrons are incredibly small and they're moving very, very fast. So it's highly unlikely they'd ever be struck. Plus, they behave somewhat like a wave and somewhat like a particle as well. There's a lot of stuff that we haven't gone into kind of yet or will that kind of says no, it's highly unlikely to strike an electron. Doesn't mean it wouldn't happen, but it's not likely. The basis to be able to split atoms was you had to have an atom that was already fairly unstable because it was fairly large. Okay, like we don't try to split oxygen atoms in a nuclear reactor for a couple of reasons. The smaller the atom, the less energy it contains when split, and the less of a target it presents. Right? There's just not enough nuclear force in a small atom to be bothered with. Okay, but radioactive things, okay, like uranium-238, which is a common nuclear fuel, is a very large, unstable atom that does release a lot. And when it breaks, its pieces it doesn't like break in half, it breaks into many pieces. Yeah. Okay, so this is this is something you'll look more at in detail, okay? But these are the orbitals that electrons can be found in according to de Broglie's electron cloud model, okay? Some of them are very close to the nucleus, okay? So here's the nucleus is this purple circle here in the middle, okay? And then there's low energy orbitals like the 1s orbital, okay, which is very, very close here, okay? And then we've got the 2s orbital, which is here, also very close. And then electrons can't really like overlap too much. They don't want to share too much in here. So there's other places where they can be, and it actually becomes this really like wonky looking shape, okay, where electrons can actually end up, right? It's not something we're going to go over here, but it is something you'll talk about in Chem 20. Electron configurations is one of the first things you do.
So like maybe in the 3s orbital that
not only just a lot of energy, but also if the atom is large and has a lot of electrons. Typically the lower orbitals are filled first and then they move out from there. So a large atom would start with stuff in that, right? Theoretically possible, yes. There's been some experiments with trying to make that happen, make electrons stop, but really essentially until you get to like absolute zero where all all kinetic molecular energy is gone, not really, no. They're going to still move around. Okay. And then another important thing here, okay, so if all atoms are made of protons, neutrons, and electrons, they're all made of the same stuff. How is it that we get different materials? Why is an oxygen atom different from a lead atom? Okay, and the answer is the number of protons in the nucleus determines the physical properties and chemical properties of a particular atom. Okay, so that's probably something that we should have underlined here. Okay. Okay, so the differing numbers of subatomic particles influence the properties of the different elements. They don't usually split directly in half. They usually break into many pieces, but then they often come back together, okay, but as something different. Because usually when that breakup happens, neutrons kind of get lost in the shuffle, okay, and they get picked up by other atoms, which is why you end up like after a nuclear reaction, you'll have different, like radioactive forms of lead, okay, is one of the things that you will often get. So, why am I not? Okay, so lead has 82 protons in its nucleus, okay? Has a atomic mass of 207, so it's got a lot more electrons, or sorry, a lot more neutrons in its nucleus. But after a nuclear reaction, we'll get a form of this that's much heavier than this, okay? Because it's going to pick up a bunch of extra neutrons, and those neutrons aren't going to stay there. They're going to come off. That's what makes something radioactive, when the atom itself loses pieces spontaneously, okay? Because when they come off at a high rate of speed. They're those particles, the X-rays and the gamma rays and things like that, that are harmful to us. When those particles move through us, they destroy our tissue.
Can you have electron, neutron, proton just by itself?
Um, well, like when a nuclear reaction happens, neutrons end up kind of being by themselves, but they don't stay by themselves for very long. Right? There's again this nuclear force that tends to pull things back together. But yeah, I mean, it's possible for an electron to be off by itself or a neutron to be off by itself, but not very often. All right, in your notes package are these questions here. Okay, they're all based on the notes that we've gone over and the stuff that I've talked about. So what I would like you to do right now is answer those questions. Complete sentences is best. Okay, those are typically the kinds of things I'll ask about in either a multiple choice or written response item on a unit exam or maybe on a quiz next week. Okay, by the way, you're not going to have a quiz on Tuesday following the May long weekend, but you can expect to have one on Thursday of next week. Okay, so what an isotope is, that's a good question. An isotope, let's say if we're talking about carbon-14, carbon-14 is an isotope of regular carbon. So normal carbon has 6 protons and 6 neutrons, normal carbon, okay? So that carbon atom would be, all right, some of these, 6 of them, would be protons and the other 6 would be neutrons. Carbon-14 is an isotope of regular carbon, and it has 2 extra neutrons, which makes it a little heavier than normal carbon, and it also makes it very weakly radioactive. It doesn't change the overall charge, right, because they're neutral. And so what we use carbon-14 for is for radio dating, like materials, right? Figure out how old they are, because carbon-14, being radioactive, breaks down at a very predictable rate. It has what we call a half-life. After a certain number of years, there'll be half as much carbon-14 as there was twice that part, right? So what we do is we know what carbon-14 breaks down into as it loses electrons. So we just look for how much carbon-14 and how much of carbon-14's breakdown product are in a material, and from that we can calculate how old it is. That just naturally occurs, yeah. Pardon me? Some forms of carbon just have that. There's a fixed percentage of each isotope of everything, right? So all things have, every element on there has different isotopes of it. The different isotopes are typically not very common. So we'd be looking at, for most things, like 95% of all atoms would be the normal kind. And then small percentages of that would be the other isotopes. Some atoms are different, but most would be that way, right? And they just kind of occur naturally. Okay, so let's have you guys working on those questions here. Okay, like I said, complete sentence answers. Does everyone have a copy of these that they can look at? I mean, I can keep moving this up and down, but they're in the notes package right after lesson 1. Yeah. Are they not there? Oh, sorry, they're in the worksheet package. Sorry. Okay. That's where, sorry, I knew I put them somewhere. Okay, so if you go to the About tab there in Google Classroom, okay, the worksheet package. And guys, honestly, I would suggest that you put that file on your phone. Like, have the Google Drive app on your phone and make that one of the things that's available offline. So it's always there. It'll load faster. If the Wi-Fi goes down, you'll still have it. Okay, it's not a huge file. So
How do we get on the Wi-Fi?
you sign in with your Isidore and your password.
When I went to sign in, it didn't work right away. I had to change a couple of visuals.
Okay.
How you get onto that? Like I use UPS.
Okay. I don't know. I just signed in with my Redeemer account and put in my password and it works.